My question is this. How many of you have been involved with a construction project of like a building, like an outbuilding or a garage or a house or, yeah. And even if you haven't been directly involved in it, how many of you have kind of watched it unfold? Could we take your so there's probably some things that you noticed, and I remodeled, I did an addition on my house. I didn't do the work, but we hired somebody to do it, and one of the things, there were two things about it that were really fun for me. One was that I learned so much. There was so much that I didn't know that I learned. That was really fun. Then the other thing that was super interesting was how much I already knew, and I didn't even realize it. Like, I just sort of picked it up, and like you all probably picked up some stuff. So here's my question. The bottom part of a structure, like a house, is often called the foundation. What do we make the foundation out of? Does anybody know? What?
Concrete?
Well, yeah, we make the foundation out of concrete. All right, seems reasonable. What about the walls, what do we make that out of?
Depending on what you're using, it's either brick or wood.
Yeah, usually, so in the old days, they would make walls of at least larger buildings out of brick. Now, most buildings have a frame that's made out of wood. If it's a really big building, like this building or a building on campus, they might use concrete or they might use metal or some combination of both. But most houses, at least around here, it's wood. And then, what about the roof? What do you put on the top?
It usually is wood and then layers with like metal or something to keep rain from getting in.
Yeah, so you got wood that's like, a surface, but then they put something on top of it. That's usually metal, or more commonly, it's what they call a composite. It's made out of like a petroleum product, kind of soft. It's almost sticky, but it holds its shape really well. And then there's like rocks and stuff embedded in it. So it's like rocks glued together with like tar on top of some sort of like plastic sheet. And so here's what's kind of interesting about that is why? I mean, if I were gonna build something and I didn't know anything, I would just pick one thing. Like, I'm gonna go to the lumber store and get a bunch of wood and then build a house out there, or I'll go to a concrete supplier and get some concrete and make that. Why would you make the foundation out of one thing, the walls out of another thing, and the roof, the top part of the roof out of something entirely different? Why do you do that? And it's a pretty obvious answer, right? But it's fun to think about these obvious things sometimes. So why? Why don't you make the foundation out of wood? Does anybody know? Yeah.
It's not sturdy enough.
Okay.
That's at least what I know of. Like, things can get into it. Wood is very, over time will decompose.
Yeah.
And that'll eventually cave in on itself.
Yeah. So one of the reasons is because that bottom part of a house, the foundation, we want it to be real sturdy. The rest of the house sits on that. So if that starts changing, then the whole house is going to change. So one thing is that concrete has a property of holding its shape. It retains its shape really well. It's very strong, and it doesn't shift too much. And then the other reason is because wood decomposes. Even if you get treated wood, eventually, if it's in contact with the ground, it will decompose. Like organs, it's bugs, right? Not real bugs, well, it can be, but more commonly, fungi will get into wood and basically eat it. And what they poop out isn't wood anymore, and so what you end up with is no wood, where there used to be wood. It just rots. It's not ideal for a foundation. So you make the foundation out of concrete. Why do they make the walls out of wood? Why don't they use concrete? I mean, if concrete is good enough for the foundation, why don't they make the walls out of concrete too? Any ideas for that? And again, this isn't a trick question, and like I said, this may be outside of your realm of experience, but most of you could probably guess a couple of things. Like, what are some disadvantages to working with concrete? Any ideas? what happens if you make a mistake? If you build a building out of concrete and you make a mistake, then you have to like knock the concrete out and re-pour it. With wood, you just pull out some nails and you could like pound a 2x4 in and be like, oops, wrong spot, and then just like take the nails out and shift it over. Wood is light. Wood is flexible, which is not good for a foundation. It is good for the rest of the house, because that way it can like move a little bit around as things shift. If the foundation drops a little bit, the rest of the house, instead of just like cracking, can kind of like bend a little bit. And if you've ever been in an older house, you've probably seen not everything lines up, right? Like the walls and the ceiling might come together and you could like, sometimes it's very clearly not a 90-degree angle. That's because like things have settled, but the house holds together. You can attach stuff to wood. So if you like pour concrete and then you want to get, you know, drywall in on the inside, it's like, what do? How do you pound a nail? I mean, you can attach stuff to concrete. There are anchors that you can use to put things in concrete. This whiteboard is like attached to this cinder block wall. But if I wanted to hang a picture, it would be a lot easier for me to do it if this wall was made out of wood than if it's made out of concrete. Put a thumbtack, you know, into wood or pound a nail into it. Whereas this, I wouldn't be able to hang something that easily. All of that stuff makes wood an ideal building material for the skeleton of a house. And then what about the roof? Why don't we use wood or concrete for the very top part? The disadvantage of that, any ideas? Yeah.
Well, it could, like, from the weather, like, chip away, like.
Yeah. So one problem is exposure. When you've got wood, even wood that's not in contact with the ground, if it's exposed to a lot of heat and light and rain, can eventually like kind of come to pieces. Yeah. What's another problem? So here's something kind of interesting. If I take this cutting board, which is made of wood, and I get some water, and I put the water on this cutting board, look, I can hold this cutting board up. I can put water on it. I have to turn the water on first. Okay, I can put water on it, and like, I'm putting a rather significant amount of water onto this cutting board, and it's just now starting to drip off, and just a little bit. Wood absorbs water. That's not great for a roof. You don't want your roof to absorb water. For one thing, you're inviting damage, like from any, like water itself might cause problems in the wood. For another thing, when things get wet, they get heavy. So you don't want like wood on the roof of a house is gonna like double its weight if it like soaks in rain. Now we can paint things, but you know, like things have to get painted every few years. So people have figured out, we'll make the foundation out of this, make the skeleton out of this, make the roof out of this. Like, we have it dialed in. We know what to build a house out of. And the reason that we do it is because of the function, the properties of the materials. When we look at chemicals in the human body, it's the same thing. The specific chemicals, the molecules that we look at, are all useful in living organisms because of the way that they function. And what we're gonna talk about today is a particular atom or element called carbon. And carbon has some really unique properties because of its structure, just like concrete or wood or the shingles on your roof. Carbon has unique properties that make it the perfect building block for all living organisms. We consider life on Earth to be something that we call carbon-based. It's highly likely that if there's life anywhere else in the universe, it's carbon-based, although we think we have an idea of what it might be if it weren't carbon-based. We think there's maybe one other element that might work. But carbon has got some like super advantages. So we're gonna look at carbon today, and we're gonna look at it in two ways. One is specifically in terms of the chemistry and biochemistry of it. That's the part I'm going to talk about. And the second piece we're going to look at is going to center on, we're going to take a detour. basically. We're gonna take a detour when we talk about carbon, and we're gonna use that as a lens into how biological organisms, including humans, have influenced huge biogeological processes on the Earth itself. In specific, today, we're gonna be looking at the carbon cycle, and on Thursday, we're gonna be looking at the greenhouse effect and how that influences climate change. So we're gonna start with chemistry stuff, and then we're gonna kind of veer off into something that's more like geology and environmental science. But then after the break, we'll come back to thinking about biochemistry specifically. So my goal is for you to think about what carbon is and where it's located on the planet. Part of the work that you do today is going to look at that second piece. I want you to understand why carbon is so important for living things. I want you to think about the carbon cycle, which is the work that you're going to be doing in the back of the classroom, and how it contributes to global climate change. That's something we'll look at a tiny bit today, but mostly we'll be thinking about on Thursday and after the break. So carbon, I'm gonna play you a little video. This is our pal, Professor Dave. And you all have probably seen Professor Dave videos before. They are, in general, pretty great. And I'm gonna just the animations are super useful. So we'll have Professor Dave show us the ropes when it comes to carbon.
Hey, it's Professor Dave. Let's talk about carbon.
He knows a lot about the science of Professor Dave Explains.
You may have heard that carbon is the element of life, but what does that mean? What determines whether an atom is of carbon in the first place? An atom consists of positively charged protons, neutrons, which have no charge, and negatively charged electrons. An element is defined by the number of protons in the nucleus. 1 proton is hydrogen, 2 is helium, 3 lithium, 4 beryllium, 5 boron, and 6 is carbon. The number of neutrons and electrons can change, but by definition, any atom with 6 protons is a carbon atom. How do they form? Hydrogen, the simplest and most abundant of all elements, accumulates into clumps due to gravity, which becomes stars. The tremendous inward pressure triggers nuclear fusion, which is when protons and neutrons smash together and fuse. Many elements, including carbon, and larger ones like iron, are made in stars. Much larger ones need the immense energy of a supernova explosion or particle accelerators here on Earth. So what's so special about carbon? Let's look at the electrons. Carbon atoms have 6. The first 2 are in the inner shell, and the other 4 are so-called valence electrons in the outer shell. These are the ones available for bonding with other atoms, which happens when 2 atoms share 2 electrons. Because elements in this part of the periodic table want to have 8 electrons in their outermost shell, carbon has a tendency to make 4 bonds. These can be single, double, or triple bonds, and with many different elements. In addition, while an atom that's bound to 2 or 3 other atoms will adopt a linear or flat shape, a carbon atom that's bound to 4 other atoms will take on a 3-dimensional shape, because that's how the electron clouds on the 4 atoms can be as far away from each other as possible. So it's the ability of carbon to bond in a wide variety of shapes with so many elements, including itself, that makes it so special. Also, carbon-carbon bonds are strong enough to be stable, but not so strong that they can't break and rearrange, which makes them excellent building blocks. When by itself, carbon has many allotropes, or ways an element can be arranged. There's the graphite in your pencil, which consists of slippery sheets of carbon that rub off easily. There's diamond, the hardest substance known, and we can even make interesting structures like nanotubes and fullerenes. That's just carbon by itself. When combined with hydrogen, oxygen, nitrogen, and a few other elements, it makes all the diverse structures in your body, including carbohydrates, proteins, and DNA. We can take nature a step further and synthesize novel materials with an array of purposes. Putting carbons in the empty spots of an iron lattice makes it stronger. We call this steel, which is used in most of the large structures we know today. Teflon, a carbon-fluorine polymer, is a non-stick substance that's highly resistant to chemical degradation. And carbon-based synthetic drugs like inhibitors that can silence a faulty enzyme hold the prospect of curing so many diseases. That's a lot of reasons to love carbon. It really is the element of life. See you next time.
If you live in Oregon, you could lower your electric bill to less than 30%.
$30 a month. That's crazy. Watch this.
It might have been 36. It might have been 36.
Okay, so he said carbon is an element, and then he started talking about atoms. And we in this class, it's not critical for us to have a distinction. In your chemistry class, it will be. When we talk about elements, elements is like a general category of things. You could think of an element as being like a category of animals, like chickens or horses or ducks. All chickens are like chickens. They're identifiable as chickens. All ducks are ducks. If you have one chicken and one duck, you can tell the difference between those two organisms. General categories we refer to as elements. The way we're going to use the term carbon is primarily as an atom. An atom is a piece of a type of matter, the smallest piece we can have. That's like the difference between chickens as a category and this particular chicken right here, which is like a specific thing. The categories are what we think of as elements. We can talk about carbon as being a category of things. And within that category, there are some slight differences. Not all pieces of carbon are the same. Each individual piece of carbon is what we call an atom. That's how we're generally going to refer to it. And then the other way that we sometimes talk about carbon is to refer to a larger substance. Like we'll sometimes say that, like the graphite in your pencil, we'll sometimes say that's carbon. Or talk about a diamond and say that's carbon. Or talk about coal and say that's carbon. It's not one small piece of carbon. It's not the general category of carbon. It's something that's mostly made up of carbon. But this is going to be our working definition. This is the one that we really need to understand. When we talk about carbon in this class, we're talking about tiny little pieces of something. It's as small as you can get and still be carbon. One specific piece of carbon. Okay? And what makes carbon so important is its structure and function. So this is kind of getting back to that whole like concrete foundation, wooden frame, shingled roofs. It turns out that carbon can make a lot of different connections. Professor Dave talked about valence electrons and electron pairs. You'll learn all that stuff in chemistry. In here, what you need to understand is that it's somewhat unusual for an atom to be able to combine with up to 4 other things. It's not typical. Most atoms can only combine with 1 or 2 things at a time. But carbon can do more. And so carbon it's a great building material for long chains because it can have so many connections. It can connect to another carbon, which can then connect to another carbon, which can connect to another carbon, and still have room for all sorts of other useful substances attached to them. The other thing that's really interesting about carbon that ends up being really useful is the shape. So when we talked about wood and concrete and shingles, we didn't really talk about their shapes, and that's partially because like wood doesn't have a shape when we look at it. Like we just see pieces of wood and we can kind of shape them as we want to. But if we were to look at the smallest piece of wood and what it looks like, it really would have a shape that's different than the smallest piece of concrete or the smallest piece of composite shingle. Shapes matter. When we talk about shapes, and we'll talk a lot more about this after the break, but when we talk about shapes, a lot of times I use tools as examples of that. These 2 tools are largely made up of the same stuff, metal and some plastic, but the shapes are very different. If I need to unscrew something or screw something in, this screwdriver is way more useful because of its shape. It's got a big handle, so I have some leverage for twisting things, and it's got a tip that's got the right shape so that it grips the inside of a screw head and I can make that turn. Whereas these channel lock pliers, this is a completely different shape. I could maybe get a screw out with this, like, if I absolutely had my life depended on it, I would try anyway, but it wouldn't work very well. But certainly if I have something that I need to like grip onto, or that if I need to turn like a pipe or a big bolt or something, this is going to be much handier. Same materials, different shapes. With carbon, the shape turns out to be really important. So we've got two things about carbon that are really key. One is the structure. It can form bonds with 4 other atoms. And so it doesn't always. It can form less bonds too, because it can do the whole double bond and triple bond trick, and you saw some of that when we were doing the building molecules activity. And then the shape. When carbon makes single bonds, it makes them in like a pyramid shape, like this. And those bonds kind of go off at angles. And what that means is you can hook carbons together and make really complicated 3-dimensional structures. Those 3-dimensional structures will have different functions. The difference between 2 molecules in your body might not be what they're made of, but it might be their shape. They might be made of the same things, but hooked together in a different way, so they do 2 different things. And that ends up being critical for living organisms. We talked last week, or maybe the week before, when we first were talking about biochemistry, about how these chemicals in our body have a few purposes. One is that they build things. They're the stuff that our bodies are made of. Another is that they store energy. And a third is that they do things. So this shape of carbon allows it to hook together in such a way that it can form the backbone of a bunch of different molecules that all do different things. Carbon is also, like all other chemical substances, when it forms bonds with other materials, it can store energy. And Professor Dave mentioned this as well. When it comes to the bond strength, carbon makes really strong bonds. I guess it's a sturdy substance, but not unbreakable. That ends up being incredibly important for living things. We talked about energy before when we were talking about food webs. We talked about the idea that energy gets stored in chemical bonds. So a plant takes sunlight and takes a little piece of sunlight and sticks it in between a couple of atoms that are held together with a chemical bond. That energy is stored in the bond. That bond can be broken. It's not easy, but it's not impossible. That releases that energy, which can then be used somewhere else for some other thing. That ability of carbon to relatively stably store energy is critical to living organisms. When you eat food, much of what you're eating ends up being used for energy. It's not like when I eat, if I eat an apple, it's not like my body takes that apple and just takes the apple stuff and just distributes it throughout my body, where I just use it the same way that the apple would. My body takes those apple pieces and breaks them apart. And it takes the energy from the apple pieces and the materials from the apple pieces, and it uses to build Dan Briegar pieces. Those are more important to me. So that reusable energy in carbon is critical. Some things store energy, they may store more energy or less energy, but sometimes things are just really impossible to break apart. There are some substances that are so stable that we can't break them apart. Here's something that's kind of crazy. For most of history, we didn't know what the covering of pollen was. Plants make pollen as part of the reproductive cycle. The skin, the shell of pollen, is so difficult to break apart that we didn't have any idea what it was until really just a few years ago, like about 5 or 10 years ago. We finally figured out what pollen is made out of. It's crazy. And then the last thing to think about is that when we attach carbon atoms together, we can make all sorts of different useful large molecules. We can make chains. We can take carbons and hook them together in really long chains. We can make rings of carbon. We can hook 5 or 6 carbons together, 4 carbons together, in such a way that they're all attached, and that ends up being a really stable substance. We can take a ring of carbon and hook it to a chain of carbons. And when we start looking in depth at the biochemical compounds that we're studying, lipids, carbohydrates, proteins, and nucleic acids, what you'll see is they're all a combination of carbon in ring forms and carbon in chain forms. Multiple carbons hooked together to make really super complicated molecules. Okay? So that's kind of the basic chemistry of carbon. You'll learn more in your actual chemistry class next year. But for today, we're going to kind of shift gears, and we're going to think about, instead of thinking about the chemistry of carbon, or even the biochemistry of carbon, we're going to think about something else. And what we're going to think about is the idea that carbon can actually be like, we can kind of keep track of where carbon is on our planet. We can look, for example, at rocks, and we can say, oh, well, if we look at the rocks in the ground, there's some carbon stored in those rocks. And we can think about, well, we also know there's like, you know, plants and animals have carbon in them. And so we can think about how our plants and animals are storing carbon. There's carbon in the ocean, in a variety of locations, and in a variety of physical like molecules, like different ways that we can have carbon stored in the ocean. And all these different places, the carbon can get there, but it doesn't necessarily stay there. So if, for example, there's carbon in a plant, part of that plant might fall off and then decompose, and that carbon might escape from the plant and go into the atmosphere as carbon dioxide. And if we have carbon in a fish in the ocean, that fish may die and then get buried in sediment, and over a really long period of time, it might be stored as carbon in like oil or coal. We can get carbon moved into rocks, we can get carbon moved into living things, we can get carbon moved into the atmosphere. We can store carbon in a variety of places, and we can move carbon around. And where carbon is largely determined by how easy it is to like get the carbon out of that thing, and how easy it is to get the carbon into that thing. If it's really easy to get carbon into something, like it's really easy to get carbon into the air, then we'll get more carbon in the air. If it's really hard to get carbon out of something, like it's really hard to get carbon out of rocks, then we'll end up with more carbon in those places. And the activity that we're going to be doing is really looking at where carbon is stored and how likely it is to stay there, and if it moves, how likely it is to go somewhere else. So we're going to use dice to kind of simulate random. Dice are like, we have random probabilities when we roll dice, right? So you're going to roll dice, and based on the roll of the dice, we're going to determine whether carbon stays in a certain spot, or if it goes, where it goes. It's going to be more likely to stay in spots that are stickier for carbon, and if it leaves, it's going to be more likely to go to spots that are easier for carbon to go to. We have 7 stations. Our stations are the atmosphere, plants, animals, soil, surface ocean, which is the top layer of the ocean, deep ocean, which is the bottom layer in the ocean, and fossil fuels. Those are laid out around the lab benches. 7 stations, there's 7 pieces of paper. Each piece of paper has 3 dice in front of it. What you're gonna do is, you're gonna start pick one. Doesn't matter which one you start with. And so let's say you start in soil. And so I'm gonna ask you to make a data table. So when you make the data table, I want you to think about what I'm doing and how I'm doing it, because ultimately you're gonna take this information and turn it into a diagram. And I'll show you how to make the diagram as well, but you gotta make the data table right first. So, so what you're gonna do is roll the dice. And the dice will either tell you, you stay here, or you go somewhere else. If you stay here, you just add a tick mark. So if I roll and it says stay in soil, then I put a tick mark. If I roll again, stay in soil, I put another tick mark. I roll again, stay in soil, I put another tick mark. I roll again, it says go to the atmosphere. So maybe a microbe, like there was a little piece of organic material in the soil and a fungal organism consumed it, digested it, and breathed out carbon dioxide. So now, that piece of carbon, that carbon atom is in the atmosphere. Roll the dice. What does it say? Stay in the atmosphere. Roll the dice again. You get respired. You have been taken up by a plant. So now I'm in plants. Roll again. You stay in the plant. 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 And roll again, and the piece of plant breaks off and falls into the ground and becomes part of the soil. So now I'm back in the soil. Then I roll again, and this time it says this little piece of carbon ended up getting compressed into a lump of coal, and now it's in fossil fuel. And then we roll and it stays in fossil fuel like, I don't know, like 6, 7 times. And then after it's been in fossil fuel 7 times, it gets burned. A person digs it up and burns the piece of coal, and it goes back into the atmosphere. When you collect your data, this is what it should look like. You're gonna have the stations, and you'll have some repeats, because you may end up, just because you start at soil doesn't mean you're never gonna end up back at soil. You're tracking one single carbon atom as it either stays in the same spot or moves to a different spot. If it stays in the same spot, you document how many rolls it stayed in that spot. That's probability. You can look up here and see, oh, well, fossil fuels was kind of hard to get out of, wasn't it? Soil was sort of tricky to get out of, so were plants. But atmosphere seemed like it was a little bit easier to get out of, at least on that roll. Like we can evaluate the likelihood of something leaving a place and where it's most likely to go when it leaves the place. So what I'm gonna ask you to do is work individually to collect data for about 15 minutes. So you'll be rolling the dice, going from station to station, recording where you are and how many times you stay there, where you go next and how many times you stay there. Almost everybody after 15 minutes will have visited each station at least once. Okay, so everybody, very likely that you're gonna visit each station at least once. Okay, and then after you've collected your data, I'll tell you what the next step is. Okay, so everybody's gonna do this individually. Does anybody have any questions? Okay,